Hello. Hello. Hey, dude. Hey, ready? Uh, okay, man. I'll just WhatsApp you one number, okay? One link. Just open that in your laptop or something. And keep the phone on, okay? Like that video has some lag, so that's why. Uh, just give me a minute. Or what? I don't understand, dude. Uh, yeah, dude, like here, a lab is open 24 hours, dude. We have the key and all, so it doesn't matter really. Internally, it's just like home, no? Whether it's holiday or not, we keep doing it. So I have something to submit by Saturday. Yeah, still working. It was full house. Everybody came yesterday. Uh, okay, so like I sent you. Are you able to see anything? Mm. Okay, okay. How's the clarity and all? Oh, okay. No, there is some delay with. Uh, okay, good, right? Mm. Yeah, I think some five. Okay, okay. Yeah. Keeping it. I'm doing that. You can see, right? Okay, this is okay, right? Okay, okay. Fine, fine. So, what are we doing? This OPAMP only will continue. Finish that. Okay. No, dude, I stopped that also. I am doing logic design now. I didn't get the momentum. Then that two-port network also I'm still struggling. I need to do. I didn't get that momentum in networks. I wanted something a little bit easier. So I just started logic design. It is going good in that. Something very easy I wanted because I'm not started. Mm. Mm. Oh, okay, okay. Uh-huh. Okay, okay, okay. Fine, fine. Mm-hmm. Yeah, we'll do open for yeah, this is turned on everything. Okay. Now, which do you want to do? You wanted? To learn op-amp only, right? Analog only or uh, okay, fine, fine. Uh, so we'll do analog. Yeah, when does office start for you? When and all, when you should leave and all? Okay, okay, okay. So half an hour will do, okay, right? 20 minutes, half an hour, yeah. Okay. Mm. So you remember last time I told this non-inverting and inverting. Is it coming inverted actually, or what? Like ulta? Oh, is it? I think resolution maybe in yours. Mm. Okay, okay. Uh, so that's what this first three things we did last time. Uh, Inverting and non-inverting. So I'll just revise it. So when you have negative feedback, uh, both the terminals act as like virtual short. Okay, it's called virtual short. This is because of like high gain, you get this virtual short. Okay, like I said, there is some theory behind it, like conceptual theory only. So like I'll just try to explain it. So assume you're having, yeah, like this. Okay. Oh, okay. Fine, fine. Okay, okay. It'll come. Don't worry. So so assume the gain is like infinity. Okay, and you're applying 5 volts. So what happens is now when you apply 5 volts, uh, so output is immediately going to go to infinity, right? So assume gain is like 1000. Okay, 1000 is fine. So 5 into 1000 is like 5000. Okay. So what happens is this goes here now. It goes to the negative terminal. Negative terminal becomes 5000. But yeah, but now what happens? This like the gain of the amplifier is the V output is like this one. It's given like this. Right? V plus minus V minus. Yeah, how much seconds is it delayed? I wrote a equation. Uh, oh, that much. Oh, okay. Hey, no, no, no. That will become a video lecture, dude. Okay. Yeah, negative. No, this negative voltage will decrease it. Okay, now. So this 5000 will decrease. So because this is inverting, right? Inverting terminal. Now, so this will keep decreasing. So assume it keeps decreasing to 4000, 3000, 2000. Now 1000 again. See, this is 5 volts here. Okay, it should equal almost like this 5 volts. So again, yeah, the input in the inverting terminal, which is nothing but the output. Uh, See, until it becomes 5 volts, it keeps decreasing. Okay, because if the voltage in the negative terminal is greater, then output will be negative, right? It should keep decreasing. So it will decrease until a point where it reaches. Difference between these two will be like what to tell. It'll equalize, dude. So then you get 5 volts in the output, like around 4.99 volts. Mm. So like for this reason, you just like think about it. Like what happens when it keeps decreasing. Okay, so you go through it, you will understand like a little bit more, and eventually this will reach like close to 5. It will not be 5. It will be less than 5 only. but will for practical reasons like theoretical reasons will approximate as same. Uh,
Okay. So once it reaches 4.9,
mhm.
then it will start again increasing, no? To try to pump the height, ideally.
Like, but I don't know how to explain this. Okay, wait, let's see.
Or will it stop at 4.9?
Okay, okay, okay. Take it like this. Okay. So wait, just um, take it like this.
Are you drawing something?
No, no, I'm not drawing. I'm just thinking.
Okay.
Mm,
So like thanking whatever you're writing, maybe some answer is send it to me.
yeah, yeah, yeah. It's okay. It's more audio only this time. Mm, just hold on a second. So dude, like you have this one. Okay. Okay, same diagram. So to get an output of 5 volt, what we should do is the question now. Okay.
Okay.
So for getting 5 volts, it means like you need to multiply in the gain into V plus minus V minus. This is the equation. Okay. Okay, it's correct, right? Output is equal to gain into difference between the two. This one. This is the op amp equation general. Okay.
Yeah.
The difference between the two terminals will be amplified and sent in the output. Okay.
Okay.
Now for this reason, so if you do by 1000, this will be around equal to like 0.005 volts. Okay.
Okay.
Now this will be the difference between V plus and V minus.
Okay.
Okay. Now if you apply like V plus something, assume you are applying some voltage, V minus should be near that only.
Okay.
To
Okay.
get five volts itself, you need to just apply 5 millivolt. That much of amplifying is there. Okay. Oh, oh, okay. So now if you convert to feedback here, it is nothing like you're applying the output itself. Okay.
Okay.
Um, mm, okay, dude, okay, just leave this dude for now. Okay. Also be 4.995. Okay. Now it makes sense little bit.
Yeah. Yeah. Yeah.
Okay. So this is called virtual short. So this you remember or what? I told last time non-inverting and inverting.
Yeah. Non-inverting, inverting. I don't
You have to apply KCL at one of the terminals. Okay, like whichever terminal has resistors.
know.
So in non-inverting, you applied like in the gap between RF and R2,
Mm-hmm. Yeah.
and inverting also same thing. Uh, is it the same? Okay, fine. See, in non-inverting differences, you okay. Just see this diagram. It's better intuition. In this diagram, like on the right, a non-inverting second figure, no.
Okay.
So you have like yeah. So you can like apply KCL in that point where R2 and RF meets,
Okay.
and and here also R2 and RF meets in inverting also. But the difference is where you give the inputs. Okay.
Okay.
So fine, you apply KCL there, you're going to get these two equations. So now we'll go for voltage follower. So voltage follower is it is basically an inverting amplifier only, non-inverting amplifier. So here like there is no equation, not much equations and all. So like if we do it, you apply KCL at any, there is, so due to virtual short, VA is equal to V minus, which is equal to V naught. Okay, so voltage follower is like the output just follows input. So that's it. There's like nothing much theory in this. Understood, right?
That's the same concept you told before, no? Negative feedback.
Yeah. Same thing. Virtual short happens. So V plus is equal to V minus. V plus is Vi and V minus is V naught. Okay, that's about voltage follower. So there are some like each amplifier has some characteristics, resistance and all those things. So that and all you leave it for now. So okay. Next is summing inverting amplifier. So here, so inverting the summer you have like in summing amplifier you have two things. Okay, one is inverting and one is non-inverting. So in inverting, obviously you will be applying the sum in the inverting terminals. The non-inverting you will be applying it in the like positive terminal. So what happens here is in inverting summer.
So, output is
Uh, so you're like assume you're applying two voltages, okay, V1 and V2. So you want the sum voltage now. Okay, like uh, the output will be the sum of the V1 plus V2 into the gain of the amplifier. Okay, so you're assuming like assume you are applying one and two. So the output should be three multiplied by whatever gain you are giving. Okay. So assume like both the resistance in the input are equal. Like assume it's R1 R1. Okay. Now apply virtual short KCL at point A, which is at virtual short point. So this is grounded because A is grounded. Assuming you have zero here. So if you just write the equation, you're going to get 0 minus V naught R of. Okay, this is, so you got the final equation. Is it visible there?
not yet. I can just see the point of
Mm-hmm. Dude, just reload the page dude once because everything the lag has increased. It should not. That day it was like 3 seconds. That's it. Just because that delay keeps like propagating. You reloaded.
now I can see the V naught is there.
Okay. So like once if you derive it, you get like this. So you can like it's clearly visible that V naught is equal to gain into the sum of V1 plus V2. Okay. So what happens is like indirectly, you, like okay, you're able to see the red pen, no? Now
Which one?
red pen,
No, no, not yet.
not yet. Okay, fine. So you have input current one, input current two. This delay is useless. Okay. So
Like
anyway,
there is 3 seconds delay at time. So that is coming now.
alright. Oh, that red pen is coming now.
No, response is not yet come.
Dude, did you reload the page?
I reloaded the page.
Oh, okay. That live button you click once, one more time.
Yeah. You can click on that, sir.
Yeah, if you click it, it goes like proper live. Okay, if you cannot click it, it means it's already live.
Okay.
Are you able to see the red things I wrote? Not yet.
No, not yet.
Okay.
Aromat.
I think internet is little slow on your side. Okay, it's fine. Just move on. Okay. So anyway, that so this what happens in this thing is like you have current on both the inputs I1 and I2,
Okay.
with each current being equal to like V1 minus 0 by R1 is I1. Okay,
Okay.
correct, right? I1 is like just the difference between the two voltages across the resistor by resistor.
Yes.
So that is I1. Down also I2. These two will go to the output section, and in this way also you can write an output like V0. You can write equation V0 is equal to I1 plus I2 divided by RF. Okay, you'll still get the same like final answer. So this is about like inverting somewhere. Any doubts in this? Keep writing because of the delay. I think I'll just write it intuitively. Just see if you can understand it. Okay.
Cool. Maybe you can first write the diagram, finish it,
Yeah,
and
yeah.
I can start it.
That's what.
You're drawing the non-inverting amplifier.
Mm.
If I increase the quality, the speed is reducing. If I decrease the quality, speed is good.
Oh, okay, okay, okay. So just keep some decent speed then better, proper.
Yeah.
Yeah, some like 360 should be enough. 240 should be enough, I feel, right?
Yeah, 240 is enough.
Mm. Okay. Just give me a second. I just forgot it. Okay, yeah, fine. We'll just apply KCL even no shortcut and all. So applying this point. Dude, I just forgot this. Okay. Any idea? You have any idea how to get the V naught equation? I'm just applying like forgot where to apply KCL. Okay, just can you give me? Hmm? What?
The non-inverting amplifier, we applied here only, no? That VI wherever you have marked.
Mm-hmm. Yeah, that only we should apply, right?
Yeah.
So ideally, what the steps is like you write the equation there,
Uh,
and you will get VI V naught in that equation, okay?
okay.
And then you substitute VI. That is the procedure. I'm thinking, what is VI here? How do we find VI as become a question? Just thinking how to find VI. What is VI? I'll just open MadeEasy. Give me a second. Okay, I just got the book itself. I'll see it up. Because this like this four diagrams are like basic, so I think we should understand that. That's why. Sorry, dude, even I didn't prepare, so it's been a while.
Our schedule is also quite hectic.
Yeah.
About from last 2 3 days, I'm able to solve only 10 problems a day.
Mm-hmm.
Not getting confidence in solving.
Dude, I did something okay, like what I did for digital because I wasn't getting momentum at all. I was not seeing progress. So I did something silly only. But it was nice. So I started solving like 10 problems in each chapter, okay, like in round robin fashion.
Okay.
Like I solved first 10, then I moved to the next chapter again, first 10. In the previous year book, I'm telling, IES book.
Okay.
Then, so once you finish the first round, you can try the second round again, second 10 questions, second 10 questions. That way, I was like covering a little bit faster. It wasn't getting bored also. And yeah, and you understood, right? Like,
Yeah. Yeah.
yeah, somewhat I felt I covered a lot more chapters in that way without what was happening is like one problem 50 questions are there. It took some 3 4 hours, and I feel like I wasn't getting into other chapters at all. That last chapter and all, like it's not it would take forever, right?
Yeah.
So then I thought, okay, we'll just start like going a little bit in every chapter.
And needs a bit of math also. The ACMR is different to
Yeah. Correct. Mm. So see what works out for you, and like try and do that one. That's what I'm telling. Like just keep experimenting, okay? If the one thing doesn't work, uh, because like if you solve at like short bursts, it's faster a little bit.
Okay.
Uh, mm, so what I think is no. Okay. So like I just tell what I remember. I just verify this, okay? Once.
Yeah. So when I'll just make short notes of it. When I'm studying, I'll go through it in detail.
Yeah. So you apply KCL at this A point, okay, as usual, like
Okay.
which we did before. And what happens in the positive terminal is you still you create a B point. So in op amp, okay, usually the current entering the op amp, it's usually very small, okay. So we can keep it like almost equal to 0. So now you apply KCL at point B. That's visible, point B.
Not it.
Okay, it is in the positive terminal. Okay, I'll just keep writing.
Yeah, I can see.
So V1 minus. So these two equations are there. Okay.
Okay.
So at T and B, I think this is correct now. So in the second equation, you will get okay. Did it come? Second equation.
Vi minus V naught by
Uh,
R is
this is at A, and the first equation is at B. Okay.
okay.
So what happens is in the eighth equation, you have to remove Vi now. That's it. Okay. You have to bring it in terms of V1 and V2.
Okay.
So in the first equation, you bring everything aside and keep vi on one side and substitute back in second equation. So you'll get a relation between v1, v2, and v0. Okay.
Okay.
So that is nothing but non-inverting summation.
Okay.
So basically, it's like uh, eventually you'll get this equation, this general equation for in non-inverting summation. V0 is equal to vi plus vi into 1 plus rf by r1. In this, you just apply the first equation at point B and you substitute back in this vi. So you just it will come, just you just see. If it makes clear, then we'll move on. So this is I kept the formula sheet. You got it?
Yeah, I got it.
Okay. So this is like general formula which gives directly second equation. Okay.
Okay.
So if you solve it also, you're going to get this. So here you just apply the first KCL at point B and you'll get a relationship between VA and V1, V2. Then you apply it back here. Okay. Okay, fine. So next is difference amplifier. So in difference amplifier, like what happens is uh, you apply input to both the terminals. Okay.
Okay.
See the problem with op amp is by default an difference amplifier. The problem is gain is too high. Okay. So if you apply 5 volts and 4 volts in one both the terminals, the difference is 1 volt. Okay. And it will get multiplied by 1000. So you get 1000 volts, which is beyond the voltage source thing, right?
Okay.
So you want to reduce the gain and all. So
Okay.
for that reason, you're using this difference amplifier. You're creating like lower end gain using negative feedback.
Okay. Okay.
So the procedure is how to find gain means so let the upper terminal like upper minus is there, and let that be point A and point B. Okay, this is down is point B. So you apply first KCL at point B, the positive terminal. Okay, find the relationship between V2 and V plus. Okay, then again you go up and apply KCL at point this negative terminal. So then you find the relationship between V1 and V minus and V naught. Okay. So now you will get now substitute V plus in V minus equation. So you will get relationship between V1, V2, and V naught. Okay. Basically KCL, dude. Okay. Just apply KCL in every terminal is there. Every terminal, joint terminals, the center points. Okay. And you will get the output equation. It's just the box is visible, right? Output equation box. Yeah, V naught is equal to, you'll get a big equation. Okay. You just solve it out, or it'll be there in the notes. And in this if the ratio of the resistances in the circuit are equal to this one, then you will get a single gain. So it will be like R2 by R1.
Okay.
So the ratio is like the ratio the so this is one branch, this is one branch. It, like consider them separately. Okay, the upper one and below one.
Okay.
So the upper branch ratio should be equal to the lower branch ratio. That's what this right side equation tells.
Okay.
Okay.
Okay. I'll see that.
So you just solve this out. This is just combination of the last two things we learned. Okay. Difference amplifier. Fine. So next we'll go to instrumentation amplifier is like it comes later. So there is one more amplifier called differential input output amplifier. Okay, this is like they ask it commonly in problems. So here, so I'll tell you what the aim of this differential input output amplifier is. Okay, so differential amplifier, its aim is to uh, like, see if like some common signal is applied to, see there are two op amps, so basically, okay, in this, fine, two op amps are there in this. Okay, and the aim of this op amp is to, if you apply same 5 volt signal to both the terminals, you should not get any gain, you should get the 5 volts itself. Okay, so it's like it should not make any changes, it should just apply whatever common signals are given, it should just give it in the output. But if any difference like different signals are given, it should modify that. So if like you're giving some 5 volt and 4 volt, that should be amplified. Okay, that's the aim here. So if common mode, if this is what I wrote here, two equations there, ACL difference and ACL common mode. So if common mode signals are applied, it should be just sent out. It should not be modified with any gain. If some different signals are sent, it should be amplified. Okay, in this ratio, this is the gain. So derivation for this is there. It is little easy only. So first of all, see this upper op amp is there, right? This plus and minus are going to be virtual short. Okay, so both are going to have V1 only. Similarly, lower op amp, both the terminals will have V2. Okay.
Okay.
Now in the output equation, output side, if you see the V naught side, so this V1 will come in top of R2 and V2 will come below R2. Okay.
Okay.
So assuming input terminals are of op amp doesn't absorb any current, then in the output side you will have the current is equal to R2 V1 minus V2 by R2. That will be the current in the output resistors
Okay.
into V1 minus V2. Okay, which is you'll get this as the gain. Is this clear?
Yeah.
Okay, fine. And hence this equation you will get. So why common mode gain is 1 means this part I'll just think it out. Okay. But this gain you understood, right? Gain this, derivation, differential
Yeah.
gain. Okay, so this is basically differential amplifier. So we'll just get back to this. We just maybe go through it once you'll understand. Okay. But basic derivation is this much only. They'll ask some problems based on. So see, everywhere it's KCL, KVL. But you apply virtual short, KCL and KVL it. So that should be enough. Common mode gain, why it is 1 even I don't remember. Maybe I'll tell you next time, or if you can go through it, it'll be good. Okay. So I'll come to the next page. We'll skip a few things and we'll go to voltage sources. Okay. So wait, just tell me when it comes. Man, no, like 15 seconds delay is there, bro, at least. It doesn't come only, yeah?
Now I can.
Okay, okay. Fine, fine, okay. Just that live button is still like, it's just, there's no touching it and all. Just try once.
Yeah, I can't do anything in life.
Okay, okay. Just try reloading once. It's in 240 only, right?
Yeah, it's in 240 only.
Okay, okay. Okay, that's fine. So anyway, that thing is visible, right? Voltage sources at least. So the point of voltage sources, okay, like, okay, just hold 1 minute. I just keep seeing the diagram and analyze. I'll just forgotten what it is. Just remember. Okay, Ruth. So now voltage source. Okay, can you hear?
Yeah, I can hear.
So the characteristics of voltage source, I'll tell how it should be means it should give a proper voltage.
Okay.
Second is its output resistance should be very less. Okay, means whatever the resistance in the terminal of the voltage source, it should be very very less. Okay, this is called loading effect and all, and like we'll come to that later. Okay? But whatever voltage source you have, ideally it should have less resistance. Fine.
Okay. Okay.
So you can use like, assume you have 5 volt and you want 2.5 volt. So
Okay.
you can just use voltage like divider to get 2.5 volt, correct? No.
Okay. Huh.
But the thing is, now voltage divider will have two resistors. So you'll be effectively getting the second resistor as the resistance, output resistance. Okay.
Huh.
So assume you'll be using some 5 kilo ohm resistor or something.
Okay.
So that's the output current. Okay. So input current is like zero because input resistance is infinity. Output resistance is zero, and you'll have some output current. Okay. So for getting this output resistance zero, you're using op amp voltage source. So the functionality is quite simple. So you have a what is this voltage follower? Okay, ideally in the first thing, just forget the resistors. You have voltage follower here. Okay.
Okay.
So voltage, whatever voltage you are getting by voltage divider, that will be just passed through the op amp. That's it. So assume VCC is 5 volts. Okay. And like the lower voltage minus VE is some 0 volts. So you want some 2.5 volt in the voltage divider between the two things. So you make R1 is equal to R2. Now the 5 volt will be split by 2 and you get 2.5 volt as the VI for op amp.
Okay.
So therefore V naught will be the same thing because voltage follower, right?
Yeah. Yeah.
So you get V naught is equal to 2.5 volts with bare minimum resistance.
Okay.
So this will not create a loading effect. So and you can you can use it in the circuit. This is about op amp voltage source. Okay.
Okay.
So any doubts in this?
No. No. Yeah. If the output resistance is less, the output voltage will also be lesser, no?
Uh, no, no, it doesn't have to depend on the resistance, dude.
But
So
V equal to IR according to that, if R reduces, voltage across the resistance will also reduce, no? Generally.
are you talking about that RL which is there here?
Yeah, the load resistance.
Yeah, see, RL is the circuit resistance. This is not there in the circuit ideally.
Okay. Okay.
Only till the op amp is the circuit. This
Okay.
RL is what do you call? Yeah. So what happens? I'll tell you. See, RL is like the circuit. Okay. So now when you add another resistance here, it becomes like parallel, right?
Yeah. Yeah.
Which means the resistance will decrease now. So the ideal resistance which you should be getting inside should be zero, so that even if it is parallel, okay, now parallel. I think it's series. Okay, fine. Series or parallel. Okay, I think it'll add up series wise. Okay, no, I'll just tell. Okay, I'll draw this diagram. Circuit. So this diagram came.
No. Okay.
Okay, wait. Just let me know when it comes. I'll see the next circuit and keep meanwhile. Dude, 20 seconds delayed. I'll too much, dude. I think read out the page once. Mm,
Let my Wi-Fi also check, so I have to do it
okay, okay.
slow this time.
Mm,
Earlier it was faster. Recently, changing it to FiberNet or something will be very fast now or something.
uh, what?
He changed the connection to
Okay,
FiberNet.
okay, okay. Fine, fine.
Changed it to FiberNet. He told it will be faster now.
Mm,
According
maybe
to
it might be
no,
YouTube problem, or I don't know. Uh, no, but what do you think? You have fast connectivity only there, or what? Good. So tell me when it's visible.
yeah, yeah, screen is stuck.
Just um,
Yeah, I can see the next one.
okay. Mm. So, so what happens now is I'll tell the like demerits of the previous circuit. In the previous circuit, the input voltage depended on the source voltage, right? The VCC. So if that changes, like some voltage fluctuation is there in VCC, the voltage divider will appropriately change the voltage itself. No, okay, you understood, right? If 5 volts become 5.5, then 2.5 will become 2.75.
Okay.
So to avoid this, you're using Zener diode. Okay, Zener diode, you know what is Zener diode?
Yes, sir. Yeah, basically, this is used for this thing of biasing and all of that.
Okay, so I'll just tell you. So every Zener diode will have its own voltage. Okay, reverse bias voltage,
Okay.
reverse breakdown voltage. So assume in this Zener diode example, you are applying 10 volts across it.
Okay.
Okay, not 10 volts across it, like mm, okay. So assume you're applying some current through it. Okay, when the current
Current.
reaches, yeah, current. So when the current reaches some high value,
Uh,
like it starts breaking down. Okay, current or voltage, anything would fine. So whatever it is. So when it becomes, so initially it will be like reverse bias. It will not conduct. After some point of breakdown voltage, there's something called breakdown region and all. Okay, it will come in electronic devices, semiconductor
uh,
level. So we'll see there. So
uh,
basically, in the final step, like after breakdown, it will maintain a stable voltage, irrespective of what voltage you apply. It will still
uh,
maintain a stable voltage. Okay.
uh,
So in this case, assume the breakdown voltage is like 5 volts.
okay.
So now whatever voltage you apply, it's going to maintain 5 volts only. That is the characteristic of Zener diode. Okay.
Okay.
Provided resistance is there series to it, some of the current manipulation will be there. Current will fluctuate, but the voltage will be constant. Okay. So if you add that to the circuit, like what you have seen, instead of R2, we have removed the previous circuit resistance, the voltage divider R2, and we have put VZ. Okay.
Okay.
Now even if VCC is like varies from 5 to 10 volts, you will still get 5 volts only here. Okay. So that is the reason we are adding VZ. And you can see one BJT in the output current, right? Output circuit.
Uh,
So what happens is the output current capacity of the default op amp is less. It is like you have in millivolts only. Okay. Microamps, I think microamps you have. But if you want more milliamperes or something, you need to use BJT, because BJT is like it can carry high current. Okay. So and BJT is a current amplifier. Okay. So if you apply microamps to the input, it will give milliamps in the output. So basically, you're adding BJT for current amplification. That's it, nothing else. Okay. So this is like advanced model of the source voltage source. So any notes in this?
no, no.
Okay. So next we have current sources. Okay, right.
Seven,
Yeah,
40. Yeah, we'll stop after current source.
yeah, that's what I was thinking. So yeah, so current sources is there. So basically, we had voltage source till now, like getting a constant voltage in the output with least resistance. So in current source, is the aim is like current should be constant and it should be independent of load resistance. Okay, load means circuit. Okay, whatever circuit you put, irrespective of that, the current should be given constantly.
Okay.
So in this circuit, you can see that RL is the load. Okay, so the aim is to make the current through RL independent of RL. Okay,
Okay.
so what happens is, see, according to virtual short, that V1 is applied again to the output itself. So the current across R1 is equal to V1 minus 0. So the current through R1 is V1 by R1, correct? Huh?
Yeah.
And that current doesn't go inside the op amp also. So it will go directly, it will keep flowing through RL.
Okay.
So you get a constant voltage which is equal to constant current to the entire output circuit, which is equal to V1 by R1. Okay. And clearly it is not dependent on RL. That's all. So for if you are using low resistance values like for R1, it means you'll get high current.
Yeah.
So you need to use BJT for that. Okay, if you're using high resistance and low current, you need BJT is not required. If you're using low resistance, high current, BJT will be required to amplify and get that voltage, that current. Okay,
Okay.
so this is current source. So yeah, I think you understood, right? Yeah, is that okay?
Got it.
Fine, fine. So I think we are halfway, 40%, I think. Wait, okay. Okay, 25% we have completed it, I think. But from now on, it will go fast because you have understood anyway, right? Some basic things and all.
So before our next connect, no, I'll just
Uh,
go through these circuits again, the notes that you have sent. No?
yeah, that
I'll
will
go.
be better, man. Yeah, that will be good. Just go through it, finished like fully, and but at least today's okay, right? You understood. I took some time, I know. This has been,
So
it's been long.